Good morning, everyone. Seems like despite having had an entire summer to upgrade all of the technical equipment in all the classrooms, they seem to have somehow made all the projector systems the least reliable that they've ever been in like the last 10 years or so. So we're still sort of stuck with these random projectors. Not that it influences you guys too much, because more or less the stuff on the screen is about the same as it would look otherwise. But hope everyone had a good weekend. I hope there is some time to digest all the stuff that's been thrown at you in the various classes over the past few weeks of the course. This is, I guess, lecture 9, so pretty much the end of week 3 worth of lectures. And what we've been talking about for the past 4 lectures or so are these forces that we can't really assess. And so we spent 2 lectures talking about dead, live, and snow loads. We went through an example of how to trace those loads down through a column, for example. Those are also going to be on joists and girders in your building. We looked at wind loads during a complete lecture, rushed through an example a little bit. And then we looked at earthquake loads in a complete lecture, rushed through an example a little bit. Stuff's going to slow down a little bit now. I kind of cram all of the load calculations into the first few lectures just so that we can get on with some of the steel stuff. You need to be able to do load calculations for this course and others. You'll see load calculations at least one more time if you're continuing on with structural engineering related courses. Today we're going to talk about something that's a bit more interesting, at least I find it interesting. We've talked about loads that actually get applied to structures. So we've got snow, it sits on the roof. That's a load that we can imagine. We've talked about wind and earthquake loads that are there at the moment in time. The wind pressure pushes on the structure. That's something that we can imagine. Today we're going to talk about something that we have to stretch our imagination for a little bit, because today we're going to be talking about something called notional lateral loads. Notional lateral loads are another kind of lateral load that we need to consider on our structure. They're not applied loads. They're not easy to imagine where they come from. In fact, the word notional, it's interesting that they picked this particular word. Does anyone know what a synonym for notional is? A synonym for notional is imaginary, okay, made up. And so it's kind of a figment of our imagination a little bit. And so I'm going to try and provide some context for exactly what it is that we're going to be talking about there in terms of what it is we're doing and what we're trying to account for in applying these notional lateral loads. The other loads that we talked about so far have been these gravity and lateral loads, dead, live, and snow, wind, and earthquake. And these are all talked about in sections of the building code. So we have 4.1.4 for dead, 5 for live, 6 for snow, 7 for wind, and 8 for earthquake loads. You're not going to see notional lateral loads anywhere in the National Building Code. And the reason for that is it's not an actual load in the sense of what we're used to thinking of in terms of loads that are applied to structures. What it actually is a technique to account for basically the stability of a structure when it has initial imperfections from the construction process, okay? And this comes up from the CSA S16 standard, because S16 as a steel standard tells us how we have to analyze the structure for the loads that come from the NBCC. Okay, so today we're going to be talking about the first little bit that comes from CSA S16. And basically after today, you should be able to describe the role of notional lateral loads in designing steel structures for strength and stability. You should be able to calculate the notional lateral loads at each floor, and we're going to see that these are primarily or exclusively things that arise from the presence of gravity loads acting on our structure. It's weird. We just talked about snow loads, live loads, dead loads acting down, right, with gravity. And basically we're going to be saying, okay, well, there's also some notional lateral loads associated with those gravity loads that we need to consider in these calculations. And ultimately, you should be able to draw the resulting lateral forces from these notional lateral loads on a free body diagram of an idealized truss system, just as we've done for all of the previous situations. Okay, does anyone have any questions about these 3 things and what they might mean for us before we get into the rest of the material this morning? Okay, so as I was quickly trying to clear the previous responses from last year, a quick poll everywhere questionnaire. I'm not sure why it shows up so small But basically what I'm going to do is I'm kind of tired. I maybe had too much fun yesterday afternoon. I'm going to lean on the wall here, okay? I don't want to carry my own weight. I'm going to be lazy. So I'm going to lean up against the wall. And there's a question here about me leaning up against the wall. And the question is, how much force am I exerting on the wall, and how much force is the wall pushing back on me to support me? Okay, so if I'm leaning over, how do I figure out, or what would be the best description of an equation that I might write to figure out how much lateral load the wall needs to push on me with so I remain standing when I'm leaning against it? We've got A, my weight, times the center of distance of my center of gravity from my foot divided by the height of my hand above the foot. We've got my weight times the distance of my center of gravity from the wall divided by height of hand above the center of gravity. And then I've got my weight over 2. And what the hell is happening right now? What is Taylor doing leaning up against the wall? And where is he going with this? So there's sort of a split, I guess, between answers A and B. There's a couple of different ways that I might figure out this force. I'm going to draw this quickly on the board just because I don't see the sense of writing absolutely everything we need to out onto the slides, and you should be able to see what's going on here. But basically, I'm going to draw a very crude stick figure of me. Okay, so I'm going to draw me. I'm standing on one leg. My other leg's up in the ground. I'm going to be pushing with my hand up against this wall, and I want to know what this force is that I need to be supported with to prevent myself from falling over. Right, so here's my foot down here. I've got, of course, the vertical force on my foot is my weight. I'm not going to use numbers because I don't need to embarrass myself here. But let's just pretend my center of gravity is somewhere here. You could idealize this more or less as well. I've got a pin here because there's some horizontal reaction and there's some vertical reaction that's helping to provide some support. I can think of this hand as a roller maybe. And so basically I've got my center of gravity, and if I take moments about my foot, which I'll call A and B, basically I can write an equation of equilibrium for a moment about my foot. That involves my center of gravity, so my weight multiplied by the distance between my center of gravity and my foot. I'll just call that X. And then I've got a distance between my foot and my hand above the wall. So I'm going to have weight times X, which is equal to a negative moment, so minus WX, plus the force acting on me multiplied by H is 0. And so I could rewrite that and say that the force required is WX, which is the weight times the distance of the center of gravity from my foot divided by H. Okay, so you're probably asking me, why are we doing a first-year statics problem for me? The next thing I might ask you is, okay, I needed this much. Let's just pretend, my arm needs to be a certain strength. And if my arm isn't strong enough, I'm going to collapse into the wall. But let's just say I'm not kind of ready to necessarily maybe lean over on the wall. I just want to know if I'm standing perfectly straight, I'm supporting myself, and I'm able to because I'm a person with a brain. And I want to know how much force somebody needs to push on me to develop the same force in my arm. Is that going to be any different from the force that develops when I'm leaning against the wall? The force that develops that I need to support myself is WX over H. And so if I was just standing here and I wanted to develop that same force in my arm to make sure it was strong enough, I'd need somebody to push on me with a force equal to WX over H, right? That's a weird thing to think about. And you might be saying, why are you talking about this? Because that's kind of weird. Well, basically, we're going to see that structures, just like I was leaning, tend to lean. You cannot ever build something perfectly straight, right? Standing straight up, if I was to try and balance my pencil in a some kind of weird, strange space world, I could perhaps balance the pencil on its tip, but ultimately it's impossible to do that. It's always going to have some lean because it's impossible for me to make it perfectly straight so that it balances on the tip. structures, you can't build them perfectly straight. And so naturally, structures are going to want to lean a little bit. And when structures are leaning, the gravity loads are going to want to push them further over. Okay, so we can think about the gravity loads here as the weight. And so the weight on a leaning structure is going to develop essentially an equivalent lateral action from the weight acting on that leaning structure. And so in addition to bracing being in a structure to resist applied lateral loads, it's also there for stability, because as structures start to lean by some distance x, there's going to be a lateral load effect from the gravity loads that want to push it over a little bit, and the brace needs to be there to help support it. Another way to think about this is maybe, right, similar to the pencil example, maybe you've been to the circus. Somebody could probably stand up on a pole and more or less balance themselves on the pole, right? Because a human is smart. You can kind of shift your center of gravity and kind of balance on a pole. I think I have a little, oh, that's a pencil. I should have a little animation here, yeah, right? He can balance himself on the pole. And so if you have a smart load sitting on something, he or she might be able to kind of sit up here and balance themselves on the pole. But if you have a block of bricks, everyone hear the saying before, dumb as a block of bricks or dumb as a pile of bricks? Pile of bricks is dumb. It can't balance itself. If you try and stand a pile of bricks on top of a post, basically there's nothing that's going to stop it from toppling over. And so we can think here of the bricks as the weight in a structure. It can be live, dead, and snow loads. And without any kind of bracing, the structure is not going to be able to stand up on its own, even under the gravity loads. So how can we turn this into something that's useful for us, instead of just talking about silly things like me leaning on the wall and trying to balance a pallet of bricks on a post? We can think of a similar problem. So let's say we've got a link, and you can think of this as a column in a structure. And let's just say it's a rigid link. It's not a beam or anything, but a truss element of some kind. We want to maybe figure out how much force or how strong does this little cable need to be to support the weight that's acting on this little link, if we can quantify how much that link is going to be leaning after construction. Okay, so somebody built this, and I mean, sure, there might be cables in a bunch of different ways, but we're simplifying the problem here. If we've got an initial lean in the structure, we'll just call it delta naught for initial displacement. We can never make that zero. And so the first question is, what is delta naught going to be? The second question is, for whatever delta naught's going to be, how much force is going to develop in that brace to support that vertical load acting on the structure if it was displaced initially in a position like this? So this is almost exactly the same problem that we just went through with me here, leaning on the wall, but it's a little bit different. Basically, if we look at some of the moments about O here, calling counterclockwise positive, everything has to be in equilibrium. We've got a force P generating a clockwise moment, so minus P times delta naught. And the only thing there to keep this thing in equilibrium is the X component, the tension in whatever this wire is, times X. So we've got minus or plus the X component, TPX times H. Right, we could rearrange this to say that the X component of the force here is equal to P times delta naught over H. And if we know the X component and we know this angle, then we could figure out how much tension is going to develop in this cable. Clear? Basically, we have a cable here. Its job is to keep this thing standing. When we have an applied force on it, it's really just there to make sure that this thing doesn't fall down, because we cannot make it perfectly straight. But if we know how much it's leaning by, we can figure out how much force is going to be developing in this cable. Does anyone have any questions about that equilibrium problem? It's a very simple equilibrium problem. You're still probably wondering why we're doing this equilibrium problem. Any questions about this concept before we continue on? Next question. Have you ever, in your life, you've modeled trusses and beams on paper since 2023 or whatever. Have you ever once in your truss said, oh, well, what if my truss is kind of leaning by an inch at every location, and then done the analysis that way? Have you ever done that before? No, the truss, it's perfect. It's straight. it's leaning up and down, or it's just plumb, it's up and down. You don't think about the imperfections that come into play from the construction or fabrication of that truss. You just say, it's standing there, and so I'm going to do my structural analysis. So this is something we could do. We could say, all right, well, let's model our trusses with some initial lean, initial displacement at every location, and then redo the structural analysis. You can do that, but it's annoying because we like to analyze structures that are perfect when they start. Okay, so what we're going to do instead, we want to know how much force needs to develop in this cable so that it stays stable when we have an initial displacement. And so if we want to know how strong the cable is going to be, but we don't want to actually analyze the leaning structure, what we're going to do is we're going to apply the equivalent horizontal force that would develop the same force in that cable. Okay, so if I model it as perfectly plumb, then I'm not going to have that displacement anymore. But if I do some of the moments about O here, some of the moments about O for this new system, to the right, or a clockwise moment, I have a force equal to delta naught P over H times H, which is equal to P delta naught. And then I've got plus the X component, TPX is 0. And so on this side, even if I do the statics for this problem, I end up with TPX, times H is equal to P delta naught over H. Okay, the statics of the problem, or at least the resulting force from the statics of the problem, we get the same answer. The force in the cable is proportional to P delta over H. It's just a different way of incorporating that load into the structure to get the same effect. Structures are not perfectly plumb. They'll have an initial lean. That's going to generate some forces in the braces we need to account for. We don't want to model the initial lean. We're just going to model it as perfectly plumb, but we need to account for that effect in some way. And how we're going to do that is by applying an equivalent or imaginary, hence the term notional, lateral load at that point. So mind-bendy enough. It's perhaps simpler than wind loads and earthquake loads, but perhaps a bit more difficult to conceptualize in what it is we're actually trying to do here. But are there any questions about this concept of an equivalent horizontal load to develop the same force in the cable there, or we could also draw the analog to bracing in buildings to account for that initial lean so that the forces end up being the same? Okay, so let's look at this in the context of a more sophisticated structure. In this class, we're dealing with steel-framed buildings, and we're talking about bracing in our structures exclusively in this course. So here we've got a structure that's leaning a little bit, and structures, like I said, they're going to lean. Now, how much they're going to lean depends on a lot of things. It depends on the quality of the fabrication. It depends on the quality of the fabricator and the contractor building the thing. But there are upper limits on how out of plumb a structure can be, and that's specified in clause 29.3.3 of the steel standard. And what it says is the maximum a column can be out of plumb is the height of that story divided by 500, or 0.2% of H. Right? This is the same as 0.2% of H. And that's the most a structure is allowed to lean. So you build a building and you're not sure. How do you determine how much the structure's leaning, do you think? Like your fabricator on site, you're just putting the pieces together. Who's going to tell you if it's leaning too much or not? You're going to hire a surveyor. And the surveyor is going to come and they're going to survey the plumbness of the column. They're going to tell you at every level how much it's out of plumb. And they're going to give you a certification of some kind. Yeah, it's in plumb, or no, it's not in plumb. And you have to straighten things out before you continue. Okay, so this is something that gets checked by surveyors in the field. It's a strict limit on the maximum amount of plumbness on our structure. And so in our case here, we might say, well, this delta naught is going to be whatever the height of my story is divided by 500. Okay, it's a small number, but it's still something that's present there. Now let's say, well, the bracing's not there. And so we're just going to say, if the bracing wasn't there, and we've got weight on each floor level, and each floor level is leaning delta naught over H, how much force is going to be required to keep that building in equilibrium? And if you apply these loads at each of the 4 floors, and you have an initial displacement delta naught over H, let's just call, or sorry, an initial displacement of delta naught, and you actually did the equilibrium, what you're going to get is you need a reaction force at each level of delta naught over h times whatever the weight at that story is. Okay, so that comes from statics, and if there was imaginary rollers up here to keep the structure in place, the reactions that would develop at those 4 rollers would be equal to those lateral forces. And now we say, okay, well, we actually want to figure out, we don't have rollers, right? We can't just put rollers in the sky and keep our structure up. That's what the bracing's for. And so if we want the bracing back in our structure, we're going to say, okay, well, if we need those reaction forces to keep the structure stable without bracing, that means that those braces should be capable of providing the same amount of force. And so we're going to apply to our structure forces of W2 delta naught over H, W1 delta naught over H, W3 delta naught over H, W4 delta naught over H. And what I guess I should clarify here is that their displacements are different potentially at each level. This is not the delta naught at the height of the structure, but it's the initial lean of each story relative to one another. Okay, so all of a sudden, we had these gravity loads that we were maybe getting a little bit comfortable with in terms of joist, girder, column forces. Now all of a sudden, we see those gravity loads popping up as lateral loads, and that might be a little bit weird, but the calculation of these loads at least is relatively straightforward because all you need is you need the weight at each level, you have the height of the story, and what would be a reasonable thing to consider for the initial displacement? If it could be anything between 0 and h over 500, what do you think a good value would be to take delta naught as? Should we say 0? No, that's not conservative. What would be the conservative thing to do? Well, there's an upper limit on what delta naught can be. We're not allowed to build structures with delta naught bigger than h over 500. So that means we should probably take delta naught of at least h over 500 to be conservative, which is 0.002 h. And so if we were to plug that back into any of these values, basically we're going to get the lateral force acting on our structure here. I might erase these and say basically we're going to get 0.002 W1, 0.002 W2, 0.002 W3, 0.002 W4, right? W times delta naught over H. If delta naught is 0.002 H, the H's cancel out, and we get 0.2% of the gravity load at each level. So we've got these lateral forces. They're acting on the floor level of the structure, right? So if I was to draw that same three-dimensional view of the floors at each level, basically we're assuming that they act at the center of the gravity of these floor systems. And then, of course, we need to figure out what the corresponding reaction forces might be at each floor level. And if we do that, we can take those loads out to each of the braced frames. And so if there was a symmetric structure with your braced frames at the two ends, this would just be half of that notional lateral force that gets applied at each floor level. Okay, so imaginary forces to generate the same effect of a real phenomena. The force is imaginary, but the reactions, the resulting internal forces are not imaginary. Okay, the brace force that develops from this is going to be a real equivalent effect that we develop by applying these imaginary lateral forces. Does anyone have any questions about that concept before we continue on? Okay. So that takes us to CSA S16, which actually tells us in section 8 how to do some stability and general structural analysis. Section 8 of the steel standard tells us what things the engineer needs to consider when they're doing an analysis of the structure, including things to prevent unstable structures from being built. And so section 8.4 specifically tells us what we need to consider with respect to the stability design of steel structures. And what the notional lateral load section of S1619 says is that at every story, the notional lateral load has to be at least 0.005 times the total factored gravity load contributed by that story, and it shall be distributed over the story in the same manner as the gravity loads at that story. Now, there are a couple of things that are in that specific sentence that are important to discuss a little bit. First of all, now we have 0.005 times, and that's more than 0.002 times. In fact, it's 2.5 times. And that comes, actually, this is more for, this whole section needs to be completely reworked in the standard, but that was to account for the fact that in moment resisting frames, there are some additional stability concerns, there are some residual stresses, there's plastification of the cross section in some locations. And so they found in one study back in like the 1990s, early 1990s, that we actually needed to apply a force of 0.005 times the gravity load at each level. Now that's to be contested. It's not 100% true, but when following this simplified analysis, we increase the factor to 0.005. If you're doing a more detailed or advanced structural analysis, you can use 0.002, but in our case, for simplified analysis, we're going to increase that number. The next thing that confuses a lot of people is that we need to apply this factor to the total factored gravity load at that story. Now, I don't like how that's described because it implies that you have to factor the gravity loads at each story and then calculate the notional lateral load. That's not correct, and what we're going to do is we're actually going to calculate the notional lateral load effects from the unfactored loads, so the loads that we calculated in lectures 5, 6. We're going to multiply those by 0.5%, and we're going to apply them with the other loads that we're going to see acting on the structure, and I'll describe that later. Where it says that they must be distributed over the story in the same manner as the gravity loads, it just means you need to consider the relative weights. If you have more load on one side of the floor than the other, the notional lateral load needs to be shifted to the center of that weight, whereas if you have a uniform load, then you can apply it in the center of gravity. The next thing it says here is that notional lateral loads have to be applied in the direction that provides the greatest destabilizing effect. What that means is the building could be out of plumb in any different direction. But what we're going to do is we're going to be assuming that the magnitude of those initial displacements is all in the same direction, and for structures overall, that generates the largest destabilizing effect such that we maximize the tension force in the bottom brace, for example. It also says notional lateral loads have to be applied in the same direction at all levels. Okay, and the last part is that when we're combining it with other lateral loads like wind or earthquake, we have to apply the notional lateral loads in the same direction as the wind or the earthquake load. Okay, so a lot of stuff kind of packed into just these two paragraphs. We're not going to be talking about three-dimensional effects in this course, but there, pardon me, there are a lot of important considerations here for analyzing our structure and including these notional lateral loads. So what does this mean for us? I've got a couple different examples here in terms of how we would break them out into different lateral forces. And so, for example, the first thing we're going to do is we're going to pick a gravity load. Maybe it's dead load. And we talked about dead loads in lecture 5. Probably we have a uniformly distributed dead load over the floor area. In our case, for our example structure, is 4.8 kPa. Okay, so we're going to have 4.8 kPa uniformly distributed over the floor. If it's uniformly distributed, the center of gravity is going to be in the center of the floor. Basically, this is going to be whatever the B dimension was over 2. Right, so if the whole width of the structure is B, we're going to apply the notional load in the center, or at a distance of B over 2. And what we're going to do is we're going to take the notional lateral loads, and we're going to say, this is 0.005 times the total dead load at this level. Same thing at the 4 levels. And whenever we apply dead loads to the structure, we're also going to apply these notional lateral forces. Okay, so these are not factored loads, they're just uniform, calculated, or specified design dead loads, and we're going to quantify the equivalent notional loads we need to apply with those loads and apply them at the same time as our gravity loads. Then we're going to go to live loads, and we're actually going to separate this out by occupancy, just like we did before. So this might be live load from office space on the interior 3 floors. We're going to include the notional lateral loads in our structural analysis alongside whatever gravity loads we have from that office level. And what's important here is because we've separated office live and roof live like we did in lecture 6 example, we're going to separate the notional lateral loads as well. And so in addition to the notional lateral load distribution for office space, we're going to have a notional lateral load at the roof level to account for that roof live load, so that we can include the effects of the roof live load in our structural analysis if we want, and exclude them if we're including our snow load, for example. Same thing for snow loads. We're going to come in and we're going to say, okay, we've got snow on the roof. There's going to be an equivalent notional lateral effect from the snow on the roof, and I'm going to get reactions acting from the floor system onto my braced frame. And so basically what I've got is, if I'm analyzing my braced frame, I'm going to have a structure model of my floor truss. And whenever I've got gravity loads acting on that truss, I'm also going to assign these 4 notional lateral loads that come in from the floor system. Over here, for my live loads, I'm going to have 3-point loads at the first 4 levels for my office live. I'm going to have a single roof live load, notional lateral load acting on the roof level of my truss. And same thing for snow. I'm going to have a single point load acting on the roof level of that truss. Okay, so when we come back here and it says total factored gravity load contributed by that story, I don't like that statement because that's ultimately what we do, but it's misleading in terms of how you try to apply them. We're going to apply the notional lateral loads calculated using the specified design values, for example, dead loads here. We're going to apply them to the structure. What's going to happen then, and we'll talk about load combinations in lecture 10 and quite a bit in lab 4 next week, about how we handle these kinds of situations when we're adding the effects of different loads together using STAD Pro or by hand calculation. Okay, are there any questions about what it is that CSA S16 is requiring from us as the engineer in terms of considering the destabilizing effects of gravity loads through the application of these imaginary lateral forces, and what other sections of the paragraph might be telling us to do? Okay. So giving a little bit more lip service, I guess, to this idea that notional lateral loads need to be distributed over the story in the same manner as the gravity loads of that story, there are a couple situations where we might not have notional lateral loads applied at the middle of the floor. And you could probably imagine these before I showed them to you. But it's possible that we might have different load intensities or an irregular plan. And so, for example, we might have half a building here that's retail or something space, and another half over here that might be office space. And basically, the effect of that is our notional lateral load is going to be shifted slightly because the centroid of these 2 loads is not going to be at the middle. It's going to favor the side of the heavier load. You can figure out where that centroid is from first year statics, right? You've got a force here. That might be live load 1, a force here. Maybe I'll call it notional live load 1, notional live load 2. You can figure out where that centroid is by taking the relative distances from one point of the 2-point loads to the other, right? NL1 times this distance plus NL2 times this distance divided by, I think it's the distance plus, the force plus force. That's going to give us the location of that notional lateral force that we need to apply at that floor level. Conversely, you can just literally only apply those 2 loads and figure out, okay, if I have a beam and I'm going to treat it as if it's simply supported, maybe instead of calculating a single notional lateral load, I'm going to calculate 1 NL1 and NL2. And then from there, you can figure out what the corresponding reaction forces or what forces would be acting on your brace frames without having to calculate the resultant total notional lateral load. Okay, so different load intensities can shift the center of action of that notional lateral force, but we also have the potential for irregular plans. And so, for example, maybe we've got an office building, but it's L-shaped. And so there's more floor space over here than there is over here. Again, we might be able to just separate that and say this is notional live load 1, and this one up here might be notional live load 2, and we could do the same thing. Whoops, I'm going ahead a little bit by accident. We could say here is the pin and roller, here's the NL1, here's the NL2, and get a slightly bigger reaction on the right-hand side that goes to the brace frame, a slightly smaller reaction on the left-hand side that goes to the brace frame. Okay, so different load intensities will change the location of the notional lateral load. And a regular floor plan will change the distribution of the notional lateral load. And as long as you account for that, then you're satisfying the statement here that the notional lateral load shall be distributed over the story in the same manner as the gravity loads at that story. Are there any questions about that concept of having a notional lateral force that's not centered, or any other considerations from that paragraph that might not be necessarily clear? Okay. The last thing I'll say, again, this is just if we have wind, for example, that we talked about in lecture 7, we've got pressure on the windward face and pressure on the leeward face. Basically, if we have wind acting this way, that notional lateral load is going to be applied in the same direction as the wind. What that means is that the tension in the brace from the notional loads, for example, will get added to the tension in the brace from the wind loads. So just to see if things stuck reasonably there, we've got another poll everywhere question here, and for some reason the text again seems to be oddly small. But we've got our 4-story example building. The dimensions are 42 by 22.5. If we were designing, I have to update this question because this was from a couple years ago, but it works still even with these numbers. If the building that we're designing has a dead load, let's say at floor 1, 2, and 3, should be 4.8 for our example, but let's just say it was 5.93. How would I figure out what the total notional force that I need to apply at 1, 2, and 3 separately? What force should I apply? 1, 2, or 3? How would I calculate that force, and what would the resulting magnitude be? The nice thing is you don't have to actually open your calculator, because I've said, okay, well, what numbers do you put together? What's the answer? I don't think there's a ladder activity you could do in the hallway at this point in time. So we've got 1, the dead load times the floor area times 0.005. We've got the dead load times the floor area times 0.05, might be a bit high. The dead load times the floor area, or the total dead load. And then we've got dead load times floor area times 0.005 divided by 2. Now be careful here, right? There are 2 answers that could be similarly applicable. What would be the total notional load at the floor? So some indecision perhaps about A versus D. Who here picked D and is comfortable talking about why? Who here picked A and is comfortable about talking about why? At least nobody picked B or C. That's great. The right answer here is actually A. And the reason for that is, again, the goal is to, again, you're not getting graded on this, but the floor area, what we want is the total notional lateral load at the floor level coming from the total dead load acting over the building. Now, if you said divided by 2, that's almost right, because that's the notional lateral load that would end up acting on the braced frame at each point. You just did a step extra and did the statics to figure out what the reaction at each side of the floor would be. Going back again down the hallway, that's fantastic. So basically what we have here, I don't think I can write on this particular slide. I can't. But what I asked you to calculate was the total notional load acting over the entire floor space, maybe N from the dead loads at level 1, 2, or 3. Let's just say 1. And we take the total floor area multiplied by the total dead load acting on the structure. And that's actually the 5,604 kilonewtons, right? That's the total dead weight at floor 1, 2, and 3. And what we need to do is we need to take 0.005% of that and apply it 0.005 times, not percent, but 0.5%, times the 5,604 kilonewtons or whatever that is. And that gives us a total notional lateral load of 28 kilonewtons acting at that floor level. If we wanted to know what the effect of that notional load was on the braced frame, that would be the 28 kilonewtons over 2, which is 14 kilonewtons 14 kilonewtons. Okay, so the effect of the notional lateral loads on the two brace frames will be that answer divided by 2, but the total notional lateral load that gets applied at that floor level is the 28 kilonewtons, which is the floor area times the dead load times 0.005. Okay, any questions about that? Any concerns about that before we continue?
Would the wards play a role?
The which, sorry?
The wards in the building, the frame plan?
Yeah, so the answer is yes. And so the question is, do these areas where there's no framing change that a little bit? The answer is technically yes. I didn't want to get into that necessarily in this course, but usually this X denotes opening. That might be for a stairwell. It might be for an elevator shaft. It might be for any reason you might have an opening there. And so technically there's probably no concrete there, but if you've got a floor, if you've got a stairwell, it's probably similar enough to the dead load that it would be similar. So the question is, it might or might not. I'm assuming for intensive purposes of this course that in terms of the opening, there's maybe some stairs and it's about the same dead load distributed over that area, but it might not be. It might have an opening that's an atrium space, or for an elevator that would change slightly the total dead load at that level. Any other questions? Okay, so let's try and do an example where there's a slightly different distribution of forces. And so this will be important for your quiz, for example. We've got this steel building. It's basically our plan or our example structure, but I'm just changing it up a little bit. Let's say that on one side there's going to be a library, on the other side there's classrooms. Maybe that's something like we've got the engineering library back here, classrooms over here. I want to calculate the total notional lateral load from the live load acting on the braced frame at column line 1. Okay, so not just what is the total notional load at the floor level, but how much of that notional load is acting on the braced frame from this floor level on that braced frame on column line 1. Okay, so I've got a braced frame on column line 1. What I want is how much force is acting there. And basically that's going to come from a combination of how much notional lateral load comes from the library and how much notional lateral load comes from the classrooms. Does anyone have any questions about what we're doing before we get into the calculations for this? Okay, so we've got some library space, and so we might just call this notional live load 1. So notional live loads that come from the first kind of occupancy here. We've got notional lateral load 2. That might be coming from the classroom space, and maybe we'd want to even consider these as separate occupancies for the purpose of doing our structural analysis, but for the example, I'll just combine them into a total effect for the purposes of calculating the notional lateral load. So the first thing is we need to calculate what these two notional loads will be for the different occupancies we have acting on the floor space. And to do that, we need to know how much live load is in the classroom and how much live load in the library. Does anyone remember what live load we designed classrooms for? 2.4, yeah. You have a different question, yeah?
When we're putting the loads in our drawing, does it matter where we're putting them for our drawing? Like where our notation load's going? Because I noticed you put it kind of in the middle, horizontally.
So like where the notional load is going to go? So the notional loads don't get shown on the drawings, but when you're doing your calculations, like basically you can put it in the middle of the floor if you've got uniform live load over the full floor area, right? Just classroom over the full floor, it's at the middle. The only times it's going to shift might be when we've got, like an example here, we've got a different live load on one side than the other, or if we've got a different shape of floor, right? Because that's going to change how much, it's changed to the distribution of the gravity load at that level. Well, it's going to be like, I'm just breaking it up here so that we can find basically the equivalent effect. So the vertical load from the library, like the centroid for the library floor is here, the centroid for the classroom floor here. You apply the notional lateral load through the same centroid as the vertical load, basically. Okay. So classrooms, yeah. So if we start with NL2, this is going to be 2.4 kPa. Anyone remember what it is for libraries? It's 7.2 for libraries. So we're going to see quite a bit more of notional lateral load to the left here. So we might say, okay, NL1, that comes from our library. That's 0.005, which is the factor we multiply the gravity load by to get the notional lateral load. We've got 22.5 meters, and then we've got 42 meters over 2, because it's half the width of the building. And so that gets multiplied by 7.2 kPa. If someone can check my math for me here, I'm pretty sure I've got the number right in this particular case. So we've got a notional lateral load from the library space of 17 kilonewtons. That's how much space. That's how much notional lateral load we're going to apply to the centroid of the library space. Questions or concerns about that calculation? The part from the classroom, same thing, 0.005 times 22.5 meters times 42 meters over 2, because it's only over half that width of the building, but times 2.4 kPa. That's going to give me a notional lateral load, I'll just say 6.7 kilonewtons. Okay, so basically notional lateral load's 3 times bigger, right? For the left side, 17 divided by 3 is 5.67. So I'm confident that these magnitudes more or less make sense. Any questions about where those two numbers come from or what they represent in terms of an equivalent lateral effect from those gravity live loads on the floor? Is that a hand? Yeah. That's a great question. Live load reduction factor. What do we do for that? The first thing is neither of these spaces can have the live load reduced, but if they could, I'll give you the right answer in lab. So what I would say first for now is do not reduce them for notional lateral loads. In fact, the building code doesn't tell us much about how we should apply a live load reduction factor for this case, and neither does F16. The answer is the lateral load effects are going to be affecting braces, for example. And if we go back to the idea that tributary area is the floor space that the element is responsible for supporting load from, then the braced frame at the left-hand side here, right, that's basically, if this was uniform distributed office space, that braced frame is going to see office live load from half of the floor level at 3 floors. And so the total tributary area might be those 3 floors. You might use that to reduce the notional load effect from live loads on that braced frame. These loads are so small, no one's going to do that in the first place. And whether or not that's appropriate or whether or not that actually meets the intent of what the notional lateral loads are for, not sure. But that's one way you could rationalize applying a live load reduction factor for that member. We'll come back to that in lab perhaps, but not super important for the course. In fact, I recommend not applying a live load reduction factor to these for now. So what does that mean? Well, that's where these loads are. So I might say, okay, how do I get that reaction? Well, I'm going to draw my simple beam, pen and roller. I've got 2 notional lateral loads. One's 17 kilonewtons, the other is 5.67 kilonewtons, and I want this reaction over here. So this is basic beam statics. I just need to know where these loads are. This load is at the center of this space, which is 1 column line away. So that's 10.5 meters. This one is 3 column lines away. So that's 31.5 meters. So I could do some of the moments about B. So I'm going to have minus 17 kilonewtons times 31.5 meters minus 5.67 kilonewtons times 10.5 meters plus the reaction at B multiplied by 42 meters. That's 0. And so that's going to give me, if I follow through that to the natural conclusion, the force on the braced frame is going to end up being equal to 14.2 kilonewtons. Okay? So what that means is I might draw a braced frame, and I had the braced frame that looked something like this. And that's at the 3rd floor. So on that braced frame, I might draw a live load notional lateral force of 14.2 kilonewtons for that floor level. Okay, so we started with the floor level. We, of course, would have the potential for live loads on the first and second floors as well. This is just to give you an example of how to do it for a single floor level. We started with loading acting over the floors. And so we said, okay, we've got library, we've got classrooms. We need to figure out what the actual load that we're going to design those areas for will be. We got 2.4 and 7.2. We take those into the notional lateral loads that represent those two spaces. So more load from the library than we get from the classrooms. We calculated the loads, did our simple beam approximation of what the floor system is doing to get the reaction at B. That reaction at B represents the force applied to the braced frame at that level from the notional live loads in our example. Last thing I'll say about this. This is not hard math, right? It's addition, subtraction, multiplication, division. It's how you set up the problem that's important. You probably learned that in statics, structural analysis, mechanics of materials. So it's not the math that we're doing that's hard. It's why we're doing the math we're doing that tends to be the more difficult concept in a course like this. Okay. Any questions about the example before we move to wrap things up? Okay, so we've basically gone through all these things. I don't know where my third one went. Last one should be draw the equivalent effect on the truss or a free body diagram of the truss. But more importantly, these are the new things today. Now you should be able to describe what the role of the notional lateral loads are for designing steel structures for the strength and stability of the building. And you should be able to calculate the notional lateral loads at each floor level, considering dead load, live load, snow load. The example notes for today's lecture include what I did here today, but they also include for our example building all the steps. So live load at each level, dead load at each level, snow load, roof live load, and it shows you how to get those forces and how to apply those loads to your free body diagram of your truss at each level along with the gravity loads. Okay, so go through that example document. Come see me if you have any questions. Other than that, does anyone have any questions about any of the stuff that we talked about today, or specifically these two new learning objectives before we wrap things up for the morning? Okay, see everyone in lab this afternoon.